Year 12, the last YouTube, well, not the last, I'm going to do another YouTube clip on exercise 5C, which is polynomials over the complex field. Now, a lot of this stuff you already know how to do, so it shouldn't be too hard, but we're going to discuss or have a look at some of these things, and it's important because it's in the syllabus documents for polynomials, and it's 7.3, and we talk about this here, the fundamental theorems or theorem of algebra. So these are our fundamental theorems, and you need to know them. Some of them will seem quite obvious, but you've got to be careful about what you state and how you state it and how you go about proving these things. So the first one is if p of x is a polynomial of degree n, where n is greater than or equal to 1, in the typing I couldn't get the greater than symbol, so n such that n is greater than or equal to 1, then p of x, this polynomial, will have at least 1 0 over the complex field. Now that sounds obvious, and when you think about these polynomials, so if we take a straight line, and there's a polynomial with a degree of 1, eventually that's going to cross the x-axis somewhere along the line. A parabola, or if it doesn't, it'll have a complex root. A parabola will have at least 1. A cubic will have at least 1. And a cubic will always have a real root. But all of these, no matter how many, and a cubic could have more, or a quartic, or a negative quartic, they're all polynomials. They're going to have at least 1 0 over the complex field, whether that's a real root or an imaginary, a complex root, it'll still be a root over the complex field. Now, a little bit of trivia for you. Carl Friedrich Gauss, remember Carl, and he's famous for adding all the numbers 1 to 100. Carl, I'll spell this wrong, won't I? Friedrich Gauss. He proved this. At age 22 in 1799. So it's been around for a while, but not that long. And that means that Mr. Gauss was a pretty clever fellow. That's just a bit of trivia for you. Okay, so the second one. If a polynomial of degree n, where n is greater than or equal to 1, again, n such that n is greater than or equal to 1, there exists the numbers c1, c2, c3, so on to the degree of n. There exists these roots, providing an out the front does not equal 0, which gives you a null polynomial, which gives you a polynomial of 0. So p of x equaling 0. So this just means, what does this mean? I'll do it again. This means that there are exactly what are you doing? Don't do that. n factors. Now they could be real or imaginary, and that p of x can be completely factorized into n linear factors. And that exactly bit is important. It means that there are exactly n factors. So if you have a cubic, there are 3 factors. One of them might be a double. One might be, you might even have a triple. You might have x minus 3 all cubed. But there are that many factors. It's a triple root. And you need to know that because you're going to factorize these things completely out. The next one, a polynomial of degree n, where n is greater than, again, n is greater than or equal to 1, has at most n distinct zeros. All right? So if it's a triple root, you can go, n minus 3, x minus 3, x minus 3, x minus 3. You can factorize out 3 times. But if the degree is greater than or equal to 1, it has n distinct zeros. That's sort of repeating the last one. You're going to find those factors. And finally, the last one, it means that you could have less. All right? That's accounting here. This is accounting this. This means there could be less. So up here in number 2, you'll say that x minus 3 all cubed, well, there's your 3 factors, but they're all the same factor, right? So this at most is important. And finally, the last one, which we already knew, and we already saw this before, that if a plus b is a complex zero of the polynomial p of x, then we'll also have a minus ib. So we'll have the complex conjugate. So we already saw this. When we find a complex root, then its conjugate is also a root. Okay, so if you look on the website, you'll see the dot points for polynomials, and this is 7.3, and these are the fundamental theorems. So how do we use this sort of stuff? Let's have a look at the exercise from 5C. We'll do an example question. So, what are you doing? Can you stop that? Stop putting things in. I'm not doing ink to shape anymore. All right, so here I go. Example number 1. And I'm pretty sure I'm just looking in Patel, and they just go in here. These are worked examples. This is the worked example number 12 on page 176. And we'll start with this. And it says factorize over the complex field x to the 4 minus 1 equals 0. Well, difference of two squares, too easy. X squared minus 1 is 1. And x squared plus 1 is the other. So that means we get x squared equals 1, so x equals plus or minus 1, and x squared equals minus 1, so x equals plus or minus root minus 1, which is, as we know, plus or minus I. So if we factorise this over the complex field, we get x plus 1, x minus 1, x plus I, x minus I equals 0. We weren't even meant to put it equal to 0. That was silly of me. We're just factorising it. We're just factorising that out. All right, let's try this next one. And that was example 12a. And this is b. And it's x cubed plus 3x squared minus x minus 3. So how do I factorise that? Well, I'm going to look at this last number here, and I'm going to try to find some factors. So what am I looking for? I'm looking for plus or minus 1 or plus or minus 3. If there are integer factors, there may not be, but let's have a go. So I'm going to try, if this is p of x, because it's a polynomial, let's try my favourite, p of 1, and we get 1 plus 3 minus 1 minus 3. Oh, 0. So, hey, love using 1. Therefore, x minus 1 is a factor. Always go 1. It's always your favourite. We'll do the synthetic division to get out the next ones. So we've got 1 there. And what have we got? 1, 3, negative 1, negative 3. There's that. Start with 1 because the lead term is 1. Okay, 1 times 1 is 1. Add them together, 4. 4 times 1 is 4. Add them together, and we get 3. 3 times 1 is 3. Add them together, 0. You're beauty. It all works out. So we can go, p of x equals x minus 1. And then what have we got here? We've got to look at these. What do we got here? We've got x squared plus 4x plus 3. And that works out really easily. X minus 1. What multiplies out to 3 and adds up to 4? X plus 3, x plus 1. And there's factorise. That's what p of x equals. What about this one? This is c. And we've got x cubed minus 1. We'll call it p of x because it's a polynomial. Well, we can go straight to the difference of two cubes, which gives us x minus 1, and we get x squared plus x plus 1. Okay, let's factorise this. Well, we're going to need x equals, going to have to use a quadratic equation, minus 1 plus or minus the square root b squared 1 minus 4ac all over 2, which is going to give me minus 1 plus or minus root 3i, I'm doing this quickly now, all over 2. So if I now factorise that, I'm going to have x minus 1. Now here we have to be careful. It's x plus minus 1 minus root 3 I over 2 and x silly. It's going to be x minus that. And x minus 1 plus root 3i over 2. And let's see how that pans out. What do I get? X minus 1, x plus 1 plus root 3 over 2i. And I'll get x plus 1 minus root 3i over 2. Is that right? Yep, that's right. So let's have a look at exercise or question 6 from 5C. So I want to do question 6 for you. I'm just double checking that one. X minus 1, x plus a half plus root 3 on 2, x plus 1 minus root 3 on 2. Yep. So here's question exercise 5C, question 6. Now, it says factorise over the complex field. 3x squared plus 2x plus 1. I'll call that P of x. Now, if I was going to use a quadratic formula here, which is what I'm going to have to do, because this is going to be a complex solution. So I'm going to use a quadratic formula, and I'm going to get x equals minus b plus or minus the square root b squared is 4 minus 4ac, 4 times 3 times 1 is 12, over 2a, which is 6. So that gives me minus 2 plus or minus root 8 negative over 6 minus 2 plus or minus 2 root 2i over 6. Let's cancel some of this. We get a 3 there and a 1 and a 1. So I get minus a third plus or minus root 2 on 3i. Now that's what x equals. But when I factorise this, 3x squared plus 2x plus 1 equals, I'm going to have x minus a third minus root 2 on 3i and x minus a third plus root 2i on 3. But because I used the quadratic formula, and you need to remember this when you're doing these, which is why I chose this question. Remember when you use the quadratic formula you are completing the square. And it's an equation. You're solving an equation. And when you complete the square, the first thing you do, the first step, is to divide by the derivative, the coefficient going too fast now, coefficient of x squared. So when you factorise, form, you must multiply by it. So we need to put a 3 out the front. And now it's in factorised form, and I'll just tidy it up. We get x plus a third plus root 2 3 on I, and x plus a third minus root 2 on 3i. Righto. Let's go back. And this is example 13. On page 176. And it says, show that x equals 1 plus I is a 0 of x cubed plus 2x squared minus 6x plus 8. Okay, and then hence factorise x cubed plus 2x squared minus 6x plus 8. Okay, if 1 plus I is a factor, well then p of 1 plus I must equal 0. So 0 equals 1 plus I cubed plus 2 1 plus I squared minus 6 1 plus I plus 8. Now I know that you guys can do that on your calculator, but it says show. So you can't be putting it into your calculator and letting that do all the work, the hard work for you. So here we go. We get, expand this, 1 plus 3i plus 3i squared plus I cubed. There's my cubic. Plus 2, 1 plus 2i plus I squared minus 6 plus 6i plus 8. Well, that equals 1 plus 3i minus 3 minus I, that's what I cubed will be, plus 2 plus 4i minus 1, because that's what, minus 2 minus 6 plus 6i plus 8. So let's get all the terms. We have a 1 minus a 3 plus a 2 minus a 2 minus a 6 plus an 8 plus a 3i minus an I plus a 4i, I'm sorry, that magically turned into a plus, minus a 6i, and here we go, 1 minus 3 is minus 2, plus 2 is 0, minus 8, 0 for that part, 3i minus I is 2i, plus 4i is 6i, plus 0, which equals 0. So we know that 1 plus I is a factor. So if 1 plus I is a factor, then 1 minus I is also a factor. That's a fundamental theorem. So we have we'll let Z equal 1 plus I. Therefore, it's a cubic. Z conjugate equals 1 minus I. We also remember x minus Z times x plus x minus Z conjugate equals x squared minus 2 times the real z's x plus zz conjugate, which will give us x squared minus 2x plus 2. So that's what x minus 1 plus I and x minus 1 minus I equals. So to finish this, to finish factorising, so that's your one part, and you know you've got a third root in there. So to finish this, to find this third root, to finish, we have two methods. Method 1, long division. So we know now we've got x squared minus 2x plus 2 into my polynomial. Where was it? X cubed plus 2x minus 6x plus 8. X cubed plus 2x squared minus 6x plus 8. This is going to be a horrible long division. We've got to we just look at the lead term, so we'll multiply by x and we get x cubed minus 2x squared plus 2x. We subtract, we're not doing synthetic, we subtract. So the x cubes go, 2x squared minus 2x, that'll give me, I'll use a different colour, 4x squared, and minus 6x minus 2x is going to be minus 8x. Look at the lead term. How do I make x squared into r mod I multiplied by positive 4x plus 4? What do I get? I get 4x squared minus 8x. Oh, and I forgot my 8. I forgot my 8 there. I forgot to bring that 8 down. 4x squared minus 8x plus 8. And when I subtract, they all go. It becomes 0. So x cubed plus 2x squared minus 6x plus 8 equals x squared minus 2x plus 2 times x plus 4. And I know that this is, what did we say? X minus that, so x minus 1 minus I, and x minus that, so it's x minus 1 plus I, and x plus 4. So a little bit of long division to finish there. But there is another method, and it's easier. So let's have a look at method 2. This is how you probably should go about doing these. Method 2. Well, we know that p of x equals x squared plus 2x plus 2 minus 2x minus 2x minus 2x plus 2 times some other root, and we don't know what that is. So we'll let alpha equal third root. Oh, we've done this before. So we get x minus alpha. And now we'll just pick some value for x. What's a good value? I know. We'll let x equal 0. So p of 0 equals 0 minus 0 plus 2, 0 minus alpha. Here we go again. 2 times negative alpha minus 2 alpha. And we know when we go back to the original equation, p of 0 also equals 0 cubed plus 2 times 0 squared minus 6 times 0 plus 8. So we know that minus 2 alpha, and by the way, that equals 8, equals 8. So alpha equals minus 4. And then when I put it in, x minus minus 4 equals x plus 4, which we got up there, which is a lot easier than doing some long division. And then eventually we can say, therefore, p of x equals x minus 1 minus I, x minus 1 plus I, and x plus 4. So, fundamental theorem of algebra. And factorizing polynomials. Remember that little note there if you use completing the square, because when you factorize it, you've got to put the number back in. and make sure you know your fundamental theorems. All right, good luck with that. And in 5C, you can look to the website to see what questions you need to